Hello everyone, I'm Yukitsuda from Yamagata University, Japan. Today I'm going to talk about this topic. We have established the electrochemical self-assembly of inorganic organic hybrid thin films as methods of obtaining concentrated functional materials. We can obtain such well-crystallized thin film of N-type zinc oxide and P-type copper thiocyanate from solutions by cathodic electrodeposition. Minor addition of organic dye into the electrolytic bath, such colored thin films are obtained due to the high loading of dye molecule into the film, and this hybridization completely changes the morphology of the film. These materials are made from smallest constituent inorganic ions and organic molecules, and they self-assemble, result in this unique nanostructure. If exchange dye molecules, they cannot be hybridized each other because they obey light chemistry between them. These hybrid materials, thin films, can be applied for dye-sensitized solar cells and electroluminescence devices. I'm studying electrochemical self-assembly, taking copper thiocyanate DS as a platform. Copper thiocyanate is wide bandgap p-type semiconductor, so often used in solar cells as hot transport layer. Cationic stilbazolium dye dust is well known to organic nonlinear optical crystals and constituted cationic DAS and anion tosylate. Copper thiocyanate can be obtained in typically such condition of cathodic electrolysis. With dust added into the electrolytic bath, hybrid thin films can be expected. In this study, I will talk about impact to crystal growth of copper thiocyanate by hybridization with stilbazolium dye and its dye loading mechanisms. First question is, what is impact of the hybridization to growth of copper thiocyanate crystal grain? On increasing concentration of dust, then change of crystal orientation, peak broadening, shift to high degrees, as well as transition of copper thiocyanate form from beta form to alpha form were observed. SEM picture shows remarkable changing of surface morphology from such large particle of copper thiocyanate to these unique nanostructure of occluded hair comb shape and scale shape were observed depending on concentration of dust in the bath. Next question is, where are these dyes located in the hybrid films? In order to check it, we did such simple experiment, soaked hybrid film into the dimethyl acetamide DMA, which is good solvent for dust but does not dissolve copper thiocyanate. Two types of hybrid materials were obtained. This one, DAS, cannot be extracted completely because DAS molecules are entrapped within copper thiocyanate crystal grains. On the other hand, all of DS can be washed away, so they are phase separated between CuSCN and DAS. So why such different hybrid structures were obtained? Amount of deposited DAS is plotted against concentration of dust in the bath. At the low dust concentration, the amount of deposited DAS steeply and linearly increases, and then levels off to show a linear increase with much smaller slope. This steeply slope suggests that this dye loading reaction is limited by diffusion of DS molecule. On the other hand, much smaller slope suggests it is limited by surface reaction limited. These different type of hybrid thin films are here and here. So we can understand these different types hybrid structures come from different dye loading reaction. Summarized above, at low concentration of dust, the dye loading reaction is limited by diffusion of DAS. So all of DAS approaching the surface then sink into copper thiocyanate. As a result, DAS is occluded into copper thiocyanate grains. On the other hand, at the high concentration of dust, DAS loading is limited by formation of complex with copper thiocyanate. Hybrid structure is reorganized by surface reaction. DAS is phase separated with copper thiocyanate and result in the unique nanostructure. So is it true that the dye loading mechanism is switched? So the reaction of electrodeposition of kappa thiocyanate can be expressed as EQ1. This reaction is completely diffusion limited reaction of complex CuSCN plus. Therefore, it can be expressed such a Levitch equation like EQ2. Assuming the Faradic efficiency of 100% for the electrodeposition of kappa thiocyanate, its rate of precipitation PCUSCN is described as EQ3. If the dye loading is diffusion limited loading, DAS rate of precipitation PDAS also should be expressed as EQ4. We already know PDAS proportional to CDAS, so we want to know effect of rotating speed of RDE. PCSCN and PDAS are plotted against C-comp and omega, for which the horizontal scaling is aligned to is the same diffusion flux density of active species when changing C-comp while keeping omega and changing omega while keeping C-comp, with CDAS equal 10 micromolar represents the condition of diffusion limited loading. PCSCN linear increase with C-comp and omega expected from EQ3. PDAS is proportional to omega as expected from EQ4, but change of C-comp gives no influence to PDAS. The same analysis has been carried out for CDAS equal 100 micromolar represents the surface reaction limited regime. Once again, PCSCN linearly increase with C-comp and omega. However, PDAS also proportional C-comp and omega, so-called PDAS dependent with PCSCN. From this data, it is revealed that the dye loading mechanism is switched depending on bath conditions. PDAS is plotted against C-comp on variation of CDAS. Vertical axis means PDAS and horizontal axis is C-comp. In the high C-comp range, PDAS is independent with C-comp and appears proportional dependence to CDAS because of the diffusion limited loading reaction. We could calculate diffusion coefficient of DAS in methanol like this. When C-comp goes below certain concentration, PDAS changes proportional to C-comp, also proportional to CDAS. The loading reaction of this regime show surface reaction limited. We are going to focus on such surface reaction limited loading regime. We propose a surface reaction loading model which one CuSCN combined to NDAS such equation like EQ5. So stability constant K should be expressed like EQ6 when insert PCSCN into EQ6. K can be rewritten as EQ7. From EQ7, we can describe relation PDAS divided by C-comp against CDAS as EQ6. And this plot shows PDAS divided by C-comp against CDAS. We did such fitting with n as a variable and then resulted n equal 0.53. It means approximately 1 DAS coordinating to kappa thiocyanate like this. And also we can calculate stability constant K as 71.9. Consequently, we could describe both loading equation diffusion limited loading and surface reaction limited loading like this. This plot shows the real data of PDAS and calculated PDAS values from each equation against CDAS in variation of C-comp. This linear red line and the curvy colorful line indicates calculated PDAS values from diffusion limited loading equation and surface reaction limited loading equation respectively. The real data good fit with calculated PDAS. Therefore, both equations indicate DS loading reaction, and it is very reasonable. Also, you can see the shifting, the switching point like this. The critical switching point between diffusion limited loading and surface reaction limited express PDS diffusion equal PDS surface like equals 9. Then we can organize this equation to the related equation between CDS and CComp like this. From EQ11, we can expect border of switching. It means when below the border, DS loading is limited by diffusion of DS. On the other hand, above the border, limited by surface reaction. As a result, the DS loading reaction can be expressed like this. These knowledge are very important to understand the electrochemical self-assembly of kappa and stilbazolium dihybrid systems. These are conclusion of my presentation and my future plan. Thank you very much for listening.